1 year ago, the Dark Energy Spectroscopic Instrument rocked the cosmology world with their Year 1 baryon acoustic oscillations results. Seemingly out of nowhere, they were finding reasonably significant evidence that dark energy is evolving. The cosmological constant was constant no more, at least when the data was combined with CMB and supernovae. Since then, we've all been waiting to know, what will 3 years of DESI BAO data tell us? And today we find out. And well, you wonderful people have all seen the thumbnail, so you know what's coming. But I'll let the DESI scientists formally break the news. What a time to be following cosmology. From DESI today, we have Cristhian Garcia-Quintero, who is a NASA Einstein Fellow at Harvard University, and Paul Martini, who is a Professor of Astronomy at the Ohio State University. Welcome, Cristhian and Paul. Do you want to start by telling us what the Year 3 BAO are saying?
If in DESI-DR1, the main message was that we were observing these tantalizing, surprising evidences in support for evolving dark energy, DESI-DR2 can be thought as we are just becoming sharper on the evidence that we are seeing. You can see that on the x-axis, we have how the dark energy behaves today, and in the y-axis, we have how the equation of a state might be evolving in time. So then this particular contour that I'm quoting here is our dataset combinations that give us the highest significance with respect to deviations away from lambda CDM, which is this actually star that we can see here. So this is where we will expect our constraints to fall if our data is telling us that it agrees with the standard model of cosmology. However, as you can see here, we are using various props to make this indication. So we have DESI BAO measurements from our second data release. We are also using supernova datasets. In particular, DSY5 is the one that gives us the highest tension. And we're also using CMB measurements from Planck PR4 and CMB lensing from Planck plus DR6. Right now, for this particular contour, we are finding a 4.2 sigma tension with lambda CDM. This is actually the plot that is going to be shown in the DESI press release. And this plot is accompanied with a very nice cartoon to make it accessible to people to know what we are referring to here. And this one was done by Claire Laman. And this cartoon here is very funny because it kind of gives you that idea and shows you a lambda that is not broken yet, but you can start seeing some cracks more and more with time. However, even though this is what will go into the press release as the main result, we have actually now this plot, which is what it is shown in the paper, and to me is the main plot that encompasses the results that we're obtaining. Because in a similar trend to DESI-DR1, we have DESI plus CMB, and we can combine that with supernova datasets. And those supernova datasets, they show some tension with lambda CDM. Depending on which supernova you pick, you will be seeing that you have a range on the significances for that tension. However, the nice thing or the novelty in this work is that even if we don't use supernova, we can see the same trends just with DESI plus CMB. So to give you some numbers here, right now we are seeing that the tensions ranges over around 3 sigma to over 4.2 sigma, depending on which supernova we consider. But even if we just use DESI plus CMB, the tension stays slightly above 3 sigma.
You said when you were showing the previous plot where you had only the green plot here, that this is the highest significance that's in the press release one. Maybe you're not making as strong a case as you can make there. The DESI-5 data is probably the cleanest supernova set as well, because it's all from the one telescope. It's the most recent one, and correct me if I'm wrong, it has the most supernovae in it.
Yeah, indeed. And actually, in particular, I mean, everyone has its own favorite, but I like DSY5 because, as you said, I mean, it is true that below redshift of 0.1, it has this historical compilation of supernovas. But if you go above that redshift, all these more than 1,600 supernovas that it has are basically just measured from DS, and then they apply a common calibration. So in principle, this is the most up-to-date data we can use. Yeah.
You're not yet looking at actual physical models beyond lambda CDM. It's still just parameterizing with W0 WA. But what would be really cool to start seeing is physical models being constrained, because maybe one of them is doing a very good job.
For this second data release, we have actually the main paper, which talks about this parameterization of WWA that it is designed precisely for this, because it looks like a Taylor expansion, but it's actually a physical calibration that is able to match the observables from actual physical theories. So if you in principle find a deviation just using this parameterization, you should take it serious. However, what we are doing in this release is that we also have various supporting papers. In particular, we have one related to dark energy extensions that go slightly beyond what we are showing in the main paper. And in that paper, we are presenting various things like going from non-parametric tests to actually constraining some actual models that are physically motivated. But as you will see once we have this released, still there is not like a clear, satisfying model that we can quote. Yeah.
So rather ironically, unlike, say, 1998, where there was a very clear, satisfying model. I mean, at least the value of lambda maybe wasn't satisfying, but the model itself, that there is a cosmological constant, is a very satisfying model that fit all the data in 1998, and immediately the new consensus becomes lambda. Right now, we don't have that situation.
There's a pretty significant difference, I think, between the lambda CDM model as it was presented and shown to work well in the late 1990s and W0WA, in that leading up to the late 1990s, there were a lot of people talking about lambda. I mean, going back to Einstein's original idea that there should be a cosmological constant, or at least there was a need for a cosmological constant. And so there were a lot of people willing to accept that there might be some property of spacetime itself that would drive the accelerated expansion. The situation for W0WA is not quite so clean, in that while there are a lot of very thoughtful models about how dark energy could evolve, there are a lot of models that would provide very different values of W0 and WA or other parameterizations completely. And there's not one clear one that we can use as the foil against lambda CDM.
At this point, I hope that people start taking more serious that we're actually seeing something. And to me, what could happen eventually if this evidence keeps growing and growing is like the job from W0WA or DCPL parameterization in pointing out that it could be something that is not the cosmical constant. That will be one thing. But once we cross, I don't know, a 5 sigma threshold, the next question will be, which is the actual model? And for that, we'll have to take a closer look in the properties of the equation state of itself. Like, for example, let's accept that there is a deviation. The next thing will be like, is there actually a crossing of the dark energy equation of state? These kind of things, they can later on inform on qualitatively on which aspects you might be thinking if you want to develop a model.
We were motivated to start the DESI project by the discovery that the expansion of the universe is accelerating. And the explanation for this acceleration is commonly ascribed to dark energy, which, while that's a great name, we don't have a good explanation for physically what dark energy is. And our hope is that higher precision measurements, especially higher precision measurements of the expansion history of the universe, will ultimately yield some physical insights into the nature of dark energy. The convincing discovery of the accelerating expansion of the universe came from observations of type 1a supernovae in the late 1990s that showed that the apparent magnitudes of these supernovae were fainter than could be explained by models where the expansion history was driven or due to matter alone, and instead required some cosmic acceleration in order to produce the observation that the supernovae were at greater distances than expected in the matter-dominated model. This figure is showing a more recent update on supernova measurements. This is showing the year 5 sample from the Dark Energy Survey, which we use in a lot of our analysis. This sample is showing that the distances to supernovae are greater than the distance for a non-accelerating universe at very high significance. Distances are really important for making this measurement of the expansion history, and supernovae are one example of a way to determine distances. They are a standardizable candle. Another method to determine very precise distances is to use standard rulers, and that's what the DESI experiment uses. We use a standard ruler that's called the BAO scale. The BAO scale is illustrated in this really nice video that was produced by some folks at the Lawrence Berkeley National Lab. The BAO scale is the distance out to which sound waves could travel in the early universe prior to recombination. And that corresponds to a scale of about 150 co-moving megaparsecs. and that makes it easy to resolve at any of the redshifts probed by DESI. The challenge is that it is a very subtle signal. As illustrated right now, it produces a very slight excess in the matter distribution at 150 megaparsec scales. And in the real universe, there's not just one BAO scale that we can measure on the sky. Instead, there are lots of overlapping scales. And this figure illustrates the challenge of trying to pull out the BAO scale in clustering analysis from a very large distribution of objects. The takeaway point is that we need enormous numbers of measurements of objects in order to measure the BAO scale at even one redshift. And that's what the DESI experiment was designed to do. The DESI experiment was built to observe enormous numbers of galaxies and quasars and use them to make the most precise measurement of the expansion history that's ever been done. We designed the DESI instrumentation to be capable of measuring 40 million galaxies and quasars in just about 5 years, which is an order of magnitude larger sample size than the previous generation dataset from the Sloan Digital Sky Survey. The DESI experiment is a multi-fiber spectrograph that is capable of measuring about 5,000 spectra at a time. And it also has incredible throughput and a robotic focal plane system that enables it to reconfigure to a new field in under 2 minutes. These three facts together make it possible for us to measure tens of thousands of redshifts in a single night. And on the best nights, we have observed over 100,000 redshifts, which is really just absolutely stunning to me. The spectra that we record from DESI are recorded on 10 bench-mounted spectrographs that we have located in a climate-controlled room at the Mayell telescope. And the climate-controlled and stable bench for the spectrographs means that the calibrations for DESI are very stable, and that helps with our sky subtraction, it helps with the overall performance, redshift accuracy, etc.
Okay, I have a super naive question now. Sky subtraction, is this basically just that the ambient light from stars, or maybe the moon, is like scattering off the atmosphere the same way that in the day I see a blue sky?
There are two components to the night sky emission that we subtract off. There is a continuum component that is produced by the effects that you mentioned, such as scattered moonlight or zodiacal dust in the solar system. There is also a component that's due to the Earth's atmosphere. The Earth's atmosphere is fortunately full of molecules, and some of those molecules produce bright emission lines. And those emission lines are in all of our spectra because we have to look through the Earth's atmosphere. And we need to subtract off those emission lines in order to detect the very faint features of our targets and measure their redshifts. At this point, I'd like to acknowledge that the Dark Energy Spectroscopic Instrument is a project that is funded by the U.S. Department of Energy Office of Science, and it is operated by the Lawrence Berkeley National Laboratory. The DESI project also has received generous funding from many sponsors and from the 72 participating institutions. The DESI DR1 dataset is now public. The DESI DR1 dataset is the dataset that was used for our cosmological results that we published last year, both on BAO and on the full shape. And that dataset includes nearly 19 million objects, including over 13 million galaxies, 1.5 million quasars, and 4 million stars. The DESI DR2 dataset, which is going to include observations up through the end of the third year of data collection, will ultimately have 40 million objects, including 30 million galaxies and quasars, and 10 million stars.
That's very exciting that data is now public. Are you going to have tutorials on how to download and use it that are shared with it?
There will be tutorials and also guides to the data sets. We also will be releasing a number of value-added catalogs alongside the release of the data themselves.
I look forward to all the future papers by the community using the data.
This figure is another view of the distance redshift relationship that we measure, but this time focused on baryon acoustic oscillations. This figure is showing along the bottom axis the age of the universe, and along the top axis the co-moving distance from the Earth, and along the left and right axes are the size of the universe today, the quantity A, and on the right the redshift. These 7 horizontal lines are marking the measurements that we have from BAO from our 7 different tracers that are in these redshift bins. And the inset panel demonstrates how our BAO measurements translate to the measurements of the BAO scale. If we're the observer, then we measure the baryon acoustic oscillation scale both transverse to the line of sight and along the line of sight. And the size of the BAO scale that we measure along the line of sight is illustrated by this set of arrows, and that's showing the size of the BAO scale along the line of sight that's proportional to the expansion rate. Whereas this is demonstrating the direction of the size measurement that we get from the transverse constraint, and that's the measurement of the transverse angular scale.
Cool. Yeah, let's get into the details of the analysis, especially what is different in DR2 compared to DR1.
So this figure is trying to tell us that we can measure the expansion history of the universe using baryon acoustic oscillations, and this will inform us along the redshift going from 0.1 to 2.1 in redshift when we measure galaxy clustering. And also we can get more information farther back in redshift from Lyman-alpha meters. But basically this figure is showing the redshift distance relationship. And so in the x-axis, we have the redshift, and in the y-axis, we have the cosmical distances. So in the top panel, you are seeing the isotropic distance scale, while in the bottom panel, you are seeing a ratio of the transverse distance divided by the distance that you measure along the line of sight. So here you can see that we have different data points that are different BAO measurements that they come from the various tracers that we have, and they are performed at a particular effective redshift. And so the color points are showing us the DESI DR2 new BAO measurements that we have, and next to them you can see these other fainter data points, which are actually the previous DESI DR1 measurements. So from here you can actually see very quickly several features. So the first one is that if you compare the two set of data points, you can see that one, the DESI DR2 BAO measurements are consistent with what we found in DESI DR1, and also that our error bars have tightened. Additionally, you can see that the lambda CDN model still provides a good fit to data. However, we leave the possibility open for other models such as WWA that can even give us a better fit to data, and actually the DESI provides some cosmic implications at that level, as I will talk later on. So as Paul was mentioning very nicely, now we have more galaxies if we consider DESI DR2 in comparison with our previous data release. However, there are other aspects where DESI DR2 is making our lives easier because it is improvement, and that can be seen from this plot precisely. This plot is using DESI DR1 data right now, but the top panels, they show the number of overlapping tiles of observations in the different time programs that DESI observe. And in the middle and in the bottom panels, we are seeing the assignment completeness for each of the DESI tracers that are being observed. So then the nice thing about this plot is like right now we have DR2, and so I can jump to the next slide and even go back and forth. So you see how this footprint, it has changed for this data release. So then this is very nice because besides having more objects and more redshifts, now we have more completeness of the sample. So that leads to a more uniform sample, and then that makes our lives easier in terms of when we need to deal to systematics. For example, when we model things like the covariance matrix, this now is easier because we have a less complex footprint, and also things like BAO reconstruction, which is this process in which we revert back the positions of the galaxies in order to enhance the BAO feature. It can become more efficient simply because we have not only more galaxies, but more completeness. Now, again, as Paul was saying, just jumping into some other details on this second data release, it was mentioning that the data release 2, it has more than 30 million galaxy and quasar redshifts and more than over 800,000 Lyman-alpha spectra from quasars. However, for our BAO measurements coming from galaxy clustering, we are only using 14 million galaxies. So most of the galaxies that we are removing, they are BGS objects. However, I am showing here in the left bottom panel the redshift distribution for our BGS sample, because now we have done some tweaks to it. So in the past, we used to use a magnitude cut on the R band that was less than minus 21.5. Now we have been a little bit more lenient, and our new magnitude cut is minus 21.35. This is very nice because it allows us to have a factor of 2 higher in the number density of the sample, while it doesn't seem to lead to a higher evolution, so it's not compromising our results. On the other hand, on the right-hand side figure, you can see the redshift distributions for all of the tracers. And these little vertical dotted lines show the redshift binning that we are using. And there are some parts of on this plot that we see that the tracers overlap, and that's when we will use a combined tracer. Let me jump to the correlation functions measurements. So as Paul was saying, what we want to detect is this sort of BO feature or BO shells once we have this 3D map of the universe that DESI provides to us, and we can do that by basically doing pair counting. And so then we are measuring the 2-point correlation function. However, here what I'm showing is that correlation function, what is decomposed into monopole and quadruple term for the various tracers that DESI measured. So then these data points that you are seeing here are the measurements of these correlation function multiples, and then you will see a BO curve that is able to fit each of these models. However, here I need to do a disclaimer, so I put a red flag for some of them. So in particular, if we start from top to bottom, if you look at the BGS sample, in that particular case, when we want to translate our BO measurements to cosmological constraints, we are only using the monopole moment. And so our final BO fit is just an isotropic fit only for this tracer. But for the rest of the tracers, we actually have 2D BO fits. And we can do this because now with more redshifts, our signal to noise is just better. So then I'm also flagging here the LRG3 and the ELG1 measurements, because these are not used or translated into cosmological parameters, but rather there we use the combined tracer, which was this portion of the redshift distribution in which you can see some overlaps. And this is very nice because by doing the combined tracer, we actually can get our tightest BO measurement among all the tracers. Indeed, the level of detection for this particular combined tracer is almost 15 sigma by now.
So just to clarify, it's not that you don't use that data, you just use it combined. So the LRG3 is not being like thrown away because of any kind of worry about its quality. It's just not being used on its own. It's being used in combination with ELG1. On the other hand, why are you not using the quadrupole?
That is a very good question, Sean. And that has to do to the internal test we did before unblinding. So as I will comment in the next slide, we did various tests, but in particularly, even though our signal to noise now is better for the BGS tracer, it is actually good enough to include to measure the quadrupole and so on. However, there are various consistency tests that we run for all of the tracers. And in particularly, when we were trying to do the 2D fit for our BAO, for the BGS tracer, when we consider the fit on different regions of the sky, we actually take a look at the North Galactic Cap and the South Galactic Cap, and then we fit BAO to both of those regions in the sky, because those are the two hemispheres that DESI is able to provide measurements, and we demand them to be consistent. So that actually was accomplished for all the tracers, but for this BGS tracer, we couldn't reach the level of consistency that we wanted, so then we just stay with the isotropic BO measurement. And actually, it is good enough because even with doing forecasts and simulations, even if we include the quadrupole, it's not that it's going to add a lot. So we just play conservative there. Yeah.
Okay, I think I had a misunderstanding. You did use the quadrupole for all the other data sets, is that right?
Exactly, just for BGS. So now, with that being clarified, and thank you, Sean, for asking that, let me jump to some other differences in the analysis. So as we already mentioned, we have more galaxies, but we want to measure a BAO. So then on that regard, what are the aspects in terms of the modeling of BAO that are different from this data release compared to the previous data released? And we have a few over here in the screen. So the first one is the new minimum scale code that we use. In the previous data release, our BAO measurements were measuring the correlation function from 50 megaparsecs over H. So right now we have kind of dropped a little bit of that information, and our new codes are starting from 60 megaparsecs over 8. So that is because when we were doing the fits to the data before blinding, we actually demand to have a good fit of the data. And with good fit, I mean the delta chi-square per degree of freedom to be below a threshold. So then if we apply this new minimum scale code, then we're able to get good fits for all the tracers. So then this is a new addition, but still it doesn't compromise the constraining power of the analysis that much. On the other hand, as we were already mentioned, we have 2D fits now for the ELG1 tracer, even though that is not used for cosmology. We rather use the combined tracer, but we actually now inform cosmology by using 2D fits on the quasar tracer, which was something that was not done in the previous data release. Another new aspect in this analysis is that we have updated our systematic error budget, in particular in 2 ways. One is that in DESI DR1, we were using a common HOD systematic errors for all the tracers, but in this release, using HOD simulations for each of the tracers, we are associating an HOD systematic error for each of the tracers, which makes our error budget just more precise. However, what might be interesting to people is that now we are adding a model of evolving dark energy in our systematic error that is related to fiducial cosmology. Because when we do the BAO fits, we actually use a template approach. And so we assume a fiducial cosmology to generate our galaxy power spectrum. And then we try to fit the BAO parameters to that. So then, as we kind of comment before in DR1, this took us a little bit of a surprise. But now, given that we know that our constraints are going to be favoring an evolving dark energy model, we have added that to our error budget as a potential deviation in our fiducial cosmology.
This is the problem with an observational science, I guess, to some extent, is that you say you're doing things blind, but because you know the year 1 results, and statistically, okay, the year 2 and 3 results are independent, but any systematics are not independent. Because I was going to ask about that. What is your fiducial model now when you say you made sure things have a good fit? Is it to lambda CDM, to W0 WA, or is it a good fit in some way that is actually cosmology independent?
Yeah, I will say that in the BAO approach, it is aimed to be close to model independent. And actually, right now, we are still using a lambda CDM model as a fiducial cosmology. However, what we are just doing now is accounting for potential deviations that we didn't have in mind before by just increasing a little bit our systematic error due to that precise effect. So it's not that it could affect the analysis in any way, but we are just inflating the error bars a little bit to be more conservative on that. Yeah.
Okay. I mean, because arguably one should be using W0 WA as the fiducial model in some way or another. I mean, it all depends on one's internal updated belief on what the correct model of cosmology is, I guess.
Yeah, no, but I think fortunately for our BAO measurements themselves, if we use a W0 WA model as a fiducial cosmology, the template approach is smart enough to kind of filter that out. So I think we are robust against that. Finally, let me just end up with this slide to refer to one of our supporting papers, that is the BAO measurements validation paper by Wender Andrade, in which all these aspects that I was just telling you very superficially, they are analyzed in detail. And actually, this paper shows a lot of tests before unblinding.
We measure baryon acoustic oscillations at the highest redshifts differently from the way we measure it at lower redshifts, because at the higher redshifts, we're able to use the Lyman-alpha forest as a probe of the matter distribution, as well as the location of the quasars that we use as backlights for the Lyman-alpha forest. Just to give some background on the Lyman-alpha forest, for those who are not familiar with it, the Lyman-alpha line is the n equals 2-to-1 transition in neutral hydrogen, and it occurs at a rest frame of 1216 angstroms. Because this line is pretty far in the ultraviolet, we're only able to observe it in redshifts above about 2 with the DESI spectrographs. The distribution of neutral hydrogen as traced by this absorption is a good match to the underlying matter distribution in the universe, so we're able to measure BAO with this amount of absorption, just like we can measure the matter distribution from quasars and galaxies. This figure is showing one spectrum from the DESI DR2 dataset. This is a quasar at a redshift of 3.2, and on the top axis is the rest frame wavelength of the quasar, and then on the bottom axis is the observed wavelength. Above a rest frame wavelength of 1216 angstroms, we see the usual quasar emission line features, the Lyman-alpha emission line from the quasar, the carbon-4 emission line, etc. And on the blue or shorter wavelength side, we see the region where there's Lyman-alpha forest absorption due to intervening neutral hydrogen in the intergalactic medium. In our analysis, we identify two regions where we measure the Lyman-alpha forest. We measure the Lyman-alpha forest in what we call region A, which is the region that falls between the quasar's emission line of Lyman-alpha and Lyman-beta. And then we identify a second region, region B, that is at shorter wavelengths than the quasar's Lyman-beta emission line. For DR2, we have approximately doubled the number of quasars in our sample at these high redshifts. And we've also obtained multiple observations of the majority of our quasars. And so therefore, in our DR2 analysis, we both have about twice as many objects and also more signal to noise per object. And that's particularly important for the Lyman-alpha measurements because then we can obtain better measurements of the transmitted flux. And the quantity that we use in our Lyman-alpha analysis is this quantity delta F, which is a measurement of the over or under density of the transmitted flux relative to the mean value.
You said that the Lyman-alpha is a good tracer of the underlying density. I guess naively one might worry, and if one wanted to know the amplitude of the power spectrum, this would be a big issue, that there'd be biases there, that it's not all of the matter, it's just the baryonic matter, but also where things are being emitted and absorbed might depend on temperatures and things like that. But for the BAO, it really is, it's like a distance scale, and I imagine the amplitude of the power spectrum is not playing a huge part or any part in your final cosmological parameters. And then it's a lot harder to think of how the Lyman-alpha could be messing up a distance scale.
That's a really good question. The Lyman-alpha absorption that we see is coming from neutral hydrogen atoms, and that's a very tiny fraction of all of the hydrogen. The intergalactic medium is ionized at a part in roughly 10,000 at these redshifts. So a very small fraction of the hydrogen is in the neutral form. And then the baryons are not necessarily perfect tracers of the underlying matter distribution either. However, since we're trying to measure the BAO peak, then we're relatively insensitive to those details. When we fit the correlation function, and I'll describe that in a moment, we do have a number of parameters that go into our model that take into account how the neutral hydrogen distribution can map to the underlying matter distribution. This is a artist's rendition of what the intergalactic medium might look like from our observatory. The telescope that's shown there is the Mayall. This is, of course, not actually to scale. This is showing how we can measure the cosmic web of the intergalactic medium. And for measuring the autocorrelation function of the forest, we correlate the amount of flux in two different locations to measure the correlation function. And we can measure that both transverse and along the line of sight. And then we also can measure the correlation function of the forest with quasars, that is the quasar-forest cross-correlation. When we combine these measurements together, we get two-dimensional measurements of the correlation function using actually 4 different correlation functions. We measure the autocorrelation of the forest in region A with itself, and that's illustrated in the top left panel. We measure the autocorrelation of the forest in region A with region B, and that's the bottom left. And then we measure 2 cross correlations. We measure the locations of the quasars relative to the forest in region A, and the quasars with the forest in region B. And the reason why we separate region A and B is that region B has somewhat lower signal to noise. We're only even able to observe the forest in region B if the quasars are at relatively high redshift. And the region B also has a number of other additional contaminants that region A does not. The details of our measurements of the correlation function are presented in our key paper, which is listed here, the DESI DR2 results. And we also have 2 supporting papers that describe the Lyman-alpha forest analysis in more detail. One thing I've realized I forgot to mention is that these 4 plots are each showing 4 measurements of the correlation function. These are actually one-dimensional projections of the underlying 2-dimensional correlation function. So in the Lyman-alpha forest, in each of these cases, we measure and fit the correlation function in 2 dimensions, and then we display it in 4 projections of that, which we call wedges, that corresponds to different regions of the 2-dimensional correlation, ranging from pretty close to along the line of sight to in the primarily transverse direction. And that's what each of these different colors corresponds to. And the mu value there corresponds to the cosine of the angle relative to the line of sight. The two supporting papers that are mentioned there are a mock validation paper that's led by Lara Casas. And this paper describes the synthetic data sets that we produced for the DESI DR2 Lyman-alpha analysis, and also all of the validation tests that we ran on these synthetic data sets, as well as we used to verify our analysis pipeline. And then the other supporting paper is led by Alison Broadzeller, and that's a paper on the damped Lyman-alpha absorber catalog. And damped Lyman-alpha systems are a particular challenge in Lyman-alpha forest analysis because the damping wings of neutral hydrogen for these very high column density systems can contaminate by lowering the flux level in a pretty large fraction of the forest for a given sightline. And so this paper describes how we identify them and also validates the completeness and purity of our measurements of the damped Lyman-alpha systems so that we can mask them appropriately in our analysis.
And the lines here are best fit to lambda CDM and best fit to W0 WA CDM. Is that correct? Or
so we fit the correlation function in 2 dimensions, and the solid line shown here is our best fit model. The best fit model is a fit to the location of the BAO peak, and then it also fits the overall shape with a number of additional nuisance parameters.
And what's the difference with the dashed line?
And the dashed line is an alternative analysis that we pursued that allowed there to be an overall broadband polynomial that also fits the overall shape of the correlation function. We found that we got consistent results in the BAO measurement whether we use this broadband polynomial or not, and so our final results is not based upon the inclusion of that additional polynomial along with the corresponding additional nuisance parameters that it would include. This figure shows the main result of the BAO measurement at redshift 2.33, and that's the effective redshift of our Lyman-alpha sample. This is showing the distance measurement along the line of sight relative to the size of the sound horizon at the drag epoch, and then along the horizontal axis, this is showing the transverse measurement, transverse co-moving distance relative to RD. And taken together, with these new results, we've achieved a statistical precision of 0.65% on the isotropic BAO scale at this redshift, which is just absolutely amazing. And for comparison, we're showing the measurement that we had from DESI DR1, and you can see the improvement in the size of the contours from DR1. We're also showing the location of lambda CDM, the CMB contour. The dashed line shows the CMB combined with the DES year 5 results with the best fit W0 WA CDM model. And this figure is meant to illustrate the complementarity of the BAO measurements with measurements from other data sets. If you look closely at this, you'll also see that there is a solid blue line that is very close to the red contours. And that represents our combined contour when we add a systematic error to our Lyman-alpha measurement. This systematic error is due to recent theoretical work that predicts a range of possible shifts of the BAO location due to nonlinear evolution. As there are several predictions that have been made in the literature, and these predictions estimate different values, we decided to incorporate this source of systematic uncertainty as just an extra systematic error rather than to estimate the value of the shift and apply it as a correction.
Okay, and it looks like that systematic error is utterly negligible compared to the statistical error.
It is very tiny, but we included it to highlight the importance of measuring it better from a theoretical standpoint because we hope that our statistical uncertainties will continue to improve, which would make this more important.
So yeah, with that being said, and the BAO measurements from both galaxy and quasar clustering and Lyman-alpha spectra being explained, now I can proceed to show the cosmical constraints and starting on lambda CDM. This figure is very nice because it illustrates that each BAO data point that was being shown in the beginning can provide cosmical constraints. In this figure, I'm showing in the x-axis the combinations H0 times RD that BAO is able to measure, and these are combinations simply because they are degenerate. But in the y-axis, I'm showing that BAO can also tell us about the matter content of the universe through omega m. And so in this plot, you are seeing the individual BAO constraints from each of the tracers, And you can observe two things here. So first of all, that if you look at all the individual constraints, they seem to be consistent among each other. And so they cover common portions of the parameter space. And the second thing is that as you go farther and farther in redshift, these degeneracy contours, they tend to tilt. So the degeneracy tends to go counterclockwise as you increase in the redshift. This is very nice because it makes measuring BAO at different effective redshifts and going farther and farther away in redshift to make the BAO measurements complementary to each other. And so when you combine them all, then you get the black contour, which is a very, very tight constraint on omega m and h naught times RD. So now we can proceed to showing the joint constraints from DESI DR2. So this plot illustrates the difference between the DESI DR1 constraints with respect to the DESI DR2 constraints. So DESI DR1 is shown in this unfilled black dash contour, while DESI DR2 is shown in the blue contour. So you can see two things here very quickly. One is that we have tighter error bars. So I can give you some numbers and tell you that in terms of the improvement on the constraints precision, now we are measuring H naught times RD and omega m with a better precision of around 40%, which is close to a factor of 2 improvement with respect to what we were measuring in DR1 in terms just of precision. The second thing is that you can observe that the DESI DR2 constraints, they are falling nearly inside the 68% region of what we were measuring with DESI DR1. And so you won't see a lot of changes in the mean value of these quantities, but rather just that the error bars tighten. As you can see here at the bottom, now we have an error bar on omega m of 0.0086. The next thing to do is that once you have the BAO measurements, that now they have become very, very precise with respect to both DESI DR1 and SDSS, is that now eventually you want to combine BAO with other cosmical probes and try to draw some conclusions from that. So then it is very interesting to just compare how DESI DR2 BAO constraints look with respect to what CMB predicts in this 2D parameter space. So very quickly, people from home here, they can see that if you just take a look at DESI DR1 and compare it with CMB, we found in DR1 that they were slightly discrepant. And then the open question was like, what's going to happen when we go to DESI DR2? Is the contour going to pull closer to CMB or not? And what we're observing is that that is not the case. And actually the current tension between DESI and CMB measurements in this parameter space has raised to 2.3 sigma. And here, just to tell again to people, CMB means data from Planck PR4 and CMB lensing from Planck PR4 and ACT DR6, which give us the most precise CMB lensing measurements. Another very interesting thing that one could do is to try to calibrate the standard ruler that we are projecting over the redshift. And to do that, one needs to inform the BAO measurements with something else. So one could either calibrate using H node or RD, but in our case, we are just doing this calibration using a BBM prior, which can inform us on omega b times h squared. And this is very nice because then you can have a take on the H naught tension by DESI and this BBM combination. So what you can see in this plot is basically, again, I'm plotting CMB, but now in the H naught omega m plane. And you can see now the constraints from DESI once you apply that BBM prior. And we got to measure for this dataset combination H naught to be 68.51 plus minus 0.58 kilometers per megaparsec per second, which is a very good precision, but however is showing a 4.5 sigma tension with shoes and a tension a little bit above 2 sigma with respect to CMB itself. However, some other very nice thing that we can do is to add to this information from theta star, which is this acoustic scale measurement that is very robust, and it comes from the anisotropies from the CMB, but is closely related to BAO. So once we add this very robust measurement at the top of DESI plus BBM, we can tighten our error bars on H naught to be 0.47 kilometers per megapixel per second, which is actually now the same precision that you obtain on H naught just using CMB. However, Another very interesting thing that you can see from this plot is that you can notice that there is this dotted black line. This dotted black line represents the degeneracy direction of a constant omega m times h cube. But this one actually, it is very relevant to CMB itself, but you can see that that direction or that degeneracy direction coincides with the degeneracy direction of the CMB plot. And actually it's under that direction in which you can see that the CMB, you can see that the DESI contours are kind of pulling away from CMB. So that direction can tell you about the tension between DESI and CMB, even if you include a BBM prior. And just to finish on this slide, just to mention that these tensions that we observe when we assume the lambda-CDN model between DESI and CMB actually can have repercussions when you look at these data sets in the W0WA model. So then these tensions that you observe in lambda-CDM are closely related to what you will get later on in dark energy. So this contour is very nice because here we can compare directly how DESI DR2 looks with respect to the previous data set that we have and the precursory survey that was measuring BAO before DESI, which is SDSS. So in the brown contour, you have the constraints from SDSS. And then in this black unfilled contour, you can see the previous constraint we derived 1 year ago using DESI DR1. And now our new constraints in blue that corresponds to DESI DR2. So this plot is very nice because it can tell you that now not only the constraints that we are obtaining with respect to DESI DR1, they have improved and they are consistent with DESI DR1, but then they are also consistent with SDSS and even more of that. Now you can actually see the improvement from DESI with respect to SDSS. Another nice thing to point out here, and something that we did in the DR1 paper, was that there was SDSS and there was DESI DR1, but we also have another data set that was the best BAO combination in terms of precision. Because for some tracers, we used to have that SDSS actually was providing you a better effective volume, which is some sort of how well you measure the BAO. So for this data release, the nice thing is that the best BAO dataset is actually coming purely from DESI because you have surpassed SDSS in effective volume for all the tracers. So now is when you can actually see the improvement.
Last year, it was a little disappointing to see the dotted black contour, but the blue one is very impressively better than SDSS. But as you said, it's great that it's not inconsistent in any way.
This improvement in DR2 relative to DR1 is especially driven by the increase in the lower redshift sample. In the DR1, our measurement precision was on order that of SDSS, whereas with DR2, we've added a lot of volume, a lot of numbers at the low redshift bins in particular, and that's the source of a significant part of this improvement.
So this slide here shows a plot for the predictions, for what the predictions of the matter content of the universe are for the different data sets that are used in this paper. So you can take a look at CMB and consider it as a pivot. And CMB predicts an omega m value close to 0.315. But then you can see that the DESI BAO DR2 measures omega m to be lower than that. And on the other hand, the supernova datasets, they all tend to measure a higher value of omega m. So then you start seeing this discrepancy on which values of the matter content of the universe each of these datasets individually prefer once you assume the lambda-CDN model. And again, this is going to end up having repercussions when you go to an evolving dark energy model.
At this point, something starts ringing alarm bells in my head, and I'll just do it by analogy. There used to be, and maybe there still is, but people have been criticizing this, a bit of an industry in Hubble tension solutions, which is where you've got the shoes large 73 value, the Planck low 67, and you have some new parameter that the best fit parameter provides H0 of 70, and then you say, look, we've detected new physics. But when you examine it carefully, neither the shoes nor the Planck actually like this parameter to be 70. You haven't actually reduced the tension, you've just found a new parameter that wants you to lie where neither data set has a good fit. And one might naively worry here that you're going to do exactly the same where you find evidence for W0WA, that looking at this, the DES supernova and the DESI BAO are in a little bit of tension here. And if you then show later on, okay, when I combine CMB plus DESI plus DES, and I find evidence for omega matter maybe being 0.32 and W0 WA, one might worry that this is actually in a region where the supernovae and the BAO are actually bad fits. So what would head that off right from the beginning would be a plot showing omega matter as best fit by DESI BAO on its own and the supernovae on their own in the W0 WA model. Because then if they're consistent before you combine the data, you're saying, no, that's fine. I can combine the data because they're consistent. But here, if one was sticking to lambda CDM, one should be anxious about combining the data. So I think I asked you this in advance, and I know you do have the plot, but
and that's the reason why we don't combine DESI with supernovas in the lambda CDM model in this paper, because they cover a very wide range of different omega m values that they prefer that are far away from the low value of omega m that DESI likes. So in this case, it is actually a very nice test to just plot the 1D posteriors for omega n when you go to this W0 WA background. So this plot here is showing that if you go to WWA, now you can see that the DESI BAO data is consistent with all the three supernova datasets, and even more than the best fit points of each of these posteriors, they kind of tend to align close among each other. And of course, you have that the error bars, they increase, but basically everything is consistent. And even if I put here the CMB contour, it will be consistent, but basically because under this model, Planck is not precisely very good at measuring omega m. So with that being said, probably I should now jump to the dark energy constraints. And for that, let me show you first this slide, in which again, I will remind the people that what we are doing here is that we are constraining deviations away from the cosmical constant by modifying the equation of state of dark energy according to this relationship, which is the so-called CPL parameterization. And it looks similar to a Taylor expansion, but this actually comes from a physical calibration of the equation of a state that is able to match within, I believe, sub% precision, the observables from actual physical dark energy theories. And so here we are measuring in the x-axis W0, which is the value of the equation of a state for dark energy today. And then we have this WA parameter on the y-axis that modulates how the equation of a state evolves in time. So then the plot that I'm showing here is just still the DESI DR1 results that we showed before. And now let me jump to the next slide to see how this has changed in DESI DR2. So here is the plot. And as you can see, there are various things that you can say. So one of them is that still, when we go to DESI DR2, DESI alone by itself, it cannot rule out by any means lambda CDM with an enough statistical significance. So it is still below the 2 sigma threshold. However, you can see that DESI DR2 is the one that is kind of choosing already a quadrant for the dark energy parameters to live in. Additionally, you can also see that as we got more data, the error bars, they have tightened up in the direction which is perpendicular to the degeneracy direction of this plot. So you can actually see improvement here, and that the preference for that quadrant still remains.
It would be cool if in the long-term future one started to see more than 2 sigma evidence in BAO alone and in supernova alone. Obviously, there's a very strong degeneracy along this line, which maybe you can explain. Is there some possible future where 0 - 1 is ruled out?
Well, what I will say is that eventually, I mean, if the evolving dark energy is actually the model of the universe, we will expect that actually DESI BAO alone just kind of goes away from that lambda CDM point. However, at this point, what we can extract from it is it's a tight constraint on this degeneracy direction, which actually, given the internal test that we have done, it doesn't have to be like this. I mean, it could be that this BAO dataset, it could actually fall with the same degeneracy direction into the quintessence region or even in another region. But this is actually what the data is telling us. And it's actually, you can think of it as a coincidence, but it is coming also from the fact that measurement on the pivot redshift is very close to what you measure to be the crossing redshift for this parameterization. So it's basically what the data is telling you. Yeah.
So maybe just to summarize, as the data gets better, it's not going to shrink this way, but it will shrink that way. But in the process of shrinking that way, it could end up ruling out WA equals 0, W naught equal -1, if the correct model is somehow not along this perfect line that does go through W naught equals -1, WA equals 0. And that would be very exciting if it did manage to happen.
Yeah, hopefully, but so now let me jump to the next slide, which are the constraints on evolving dark energy, but showing the previous plot that got very popular from the DR1 release. That is showing the combination DESI plus CMB plus the different supernova datasets that we have. And now I'm going to show you how this plot has changed since 1 year ago, where the results were presented in the APS meeting. So there you go. So now what we can see in this release is that since DESI now doesn't favor this region of the parameter space, then the contours for these combinations, they have moved into this way. So what this leads to is that now we have seen that the tensions still not only remain, but they have marginally increased. For all of the supernova datasets, the tension has now increased by a 0.3 sigma with respect to the previous DR1 results. So then, just to summarize on this, the tension when you combine DESI plus CMB is now 2.8 if you use Pantheon plus, so that is very close to the 3 sigma threshold. And then if you use rather union 3, then your tension is 3.8 sigma, so it's close to the 4 sigma threshold. But now we have that even we can go above the 4 sigma threshold, because if we use DSY5, then we get a 4.2 sigma tension. So then this is how the constraints have moved, and is gradually increasing. On the other hand, something very nice, and as I said before, it's kind of the novelty again from this paper, is that it's not only that with the DR2, you are seeing that the constraints are marginally increasing with respect to lambda CDM, but also now, even without supernova, you are able to tell that there is a tension above 3 sigma with respect to lambda CDM. And that is, to me, very, very, very telling, because the big controversy in DR1 was which supernova dataset I choose. So now, even if you don't choose any supernova, then you are finding indications that there is a tension above 3 sigma with lambda CDM. And the precise number here is 3.1 sigma. So it's very nice also because the DESI plus CMB contours, they fall into these regions where you can see that there is some common portion of the parameter space covered by the 4 datasets. And however, as we were commenting before, I mean, it is that now DESI plus CMB is above the 3 sigma tension because actually DESI didn't like this part of the parameter space. So it is actually what the data is telling you.
Maybe just quickly comparing to the Hubble tension and solutions to the Hubble tension again. What's also compelling here, I think, and correct me if I'm about to say something wrong, but if you treat the data sets as independent, the best fit combined area actually does have a better fit individually. Like, sure, DESI on its own is consistent with W naught equaling -1, WA equaling 0, but the best fit value is in this quadrant. So you're not, by combining the data, again, I mean, I'm dwelling on the same point, but you're not forcing the individual data sets into worse fit regions of parameter space for them individually. You're actually moving into the better fit regions of parameter space.
Yeah, no, that's right, Sean. I think that is a very good point. So if you look at the individual contours by themselves, you will see that, for example, all of them allow this region to give a reasonable fit. So then there is a common part of the parameter space where actually they are jointly pulling towards. So yeah, that is the case. On the other hand, something very nice that we did for this data release and was not present in the previous DR1 results was to try to assess the robustness against the dark energy results that we are obtaining. Why? Because simply in DR1, it took us a bit of a surprise. So now we have more time. So then we have included various effects. So for example, in this plot that I'm including here, you can see how the constraints change on the combination DESI plus CMB if you start to take out some effects that affect the CMB. Why? Because now the DESI plus CMB contour by itself is very relevant. So then now we are just studying variations along that line. So then the green contour here shows how the constraints change if you remove CMB lensing. So it actually diminishes a bit the significance. You are taking away some data, but it's not like you're changing the behavior of the constraints dramatically. And even more, we can use what I call a compressed prior on CMB, in which you remove any late time physics phenomena from CMB, such as CMB lensing and things like late ISW, and just informing DESI given a correlated prior on theta star, omega B, and omega BC. And just with that, you are able to reproduce the behavior from CMB. And of course, you pay the price to get a little bit less tension. However, you can see that this tension that you're observing from DESI and CMB, even if you use these simple priors, it is actually present. So then this is very nice. Also because this compression aims to be independent of the late time universe model that you assume. So then this is a very nice indication that we are robust against that. On the other hand, we have also done other testings on the line of supernova data. Because, as you know, there is certain controversy, depending who you ask, on calibration in the supernova datasets, for example, in the DS Wi-Fi survey. So what we did here is that we have removed the samples for this supernova that belong to redshift less than 0.1, and we had just keep with the single observations from the DS Wi-Fi survey. So what you can observe here is that once we drop the low redshift supernova, which again, ideally one should not, because that is informing very powerful about the dark energy, because we are very sensitive to that on those redshifts. But if you do that, you will see that the contours inflate, and of course your tension with lambda CDM diminishes, but it's not like the contour is kind of pulling all towards that region, but rather the best fit is still on the region that you find if you consider the whole combination. So it seems to be robust even against that. Yeah. So now another thing that we did as well is replacing the CMB with the DSY3 3x2 point data, which is more related to clustering and weak lensing primarily. So then this is very nice because we can replace the CMB and put here DSY3 3x2 point, and then we get a constraint on the equation of state parameters that is purely dependent on low redshift props. So then if we do that, actually, what we'll get is this orange contour here, which is the combination DESI plus DS Wi-Fi supernova and DESI, and DSY3 3x2 point. This is very nice because even though it's less constraining than if you use CMB, you can still see that the same region of the parameter space is preferred, but also a very important point is that usually we tend to see that all the contours, they point towards lambda CDM, but in the case of this contour, you see that for some reason it is pointing a little bit different. So then it is very nice to see also that there might be other data sets that might change that a bit. Yeah.
And it's what's also compelling is you've now got evidence for evolving dark energy without the supernova and without the CMB.
Exactly. Of course, with a different trade-off in significance, but yeah, that is the case. And even that we have gotten a data set that it doesn't have to do with the early universe directly. And finally, something that we did in DR1, and we just have repeated the test here, is that we can actually use alternative CMB livelihoods, still using Planck, and see that our results are robust to that. On the other hand, something extra that we have done this time was to perform a binning on the equation of a state of dark energy. So this is very nice because our results assume this W0W parameterization. But here what we are doing is just measuring indirectly measuring the equation of a state within each redshift bin and telling us what the data prefers the equation of a state to be. So what you can see in this figure is that, of course, our error bars kind of inflate as we go further in redshift. However, at redshift below 1.5 or so, you can see that what we find the constraints to be from the binning method, they are fairly consistent with what we find with our W0W parameterization. And so this should be very reassuring because we are seeing a consistent picture. And I would refer people to see more details about this non-parametric test and some others in this paper by Kushal, which is our dark energy supporting paper.
You even see the crossing, which is very compelling.
Yeah, indeed. I mean, I can comment on that. So this can be also a big of a debate, but related to the crossing, which, as you say, if one look at the pictures, you see that there is it is very tempting to say that there is some crossing potentially going on there. So I will say on that regard that what we can observe with beating is that at very low redshift, we have a very tight error bar. So that can help us to confirm, and sorry if I didn't mention, but this is for the DESI plus CMB plus DES Wi-Fi combination. But you can see that the error bars at low redshift are very tight, and the binning method is actually pointing that there is a very high tension on that particular bin. However, as you go to the next bin, you can see that it is pulling the constraints to lower values of W. However, the error bar is still a little bit big. On the other hand, this question of the crossing can be very tricky because there might be scenarios where you cannot claim with a lot of confidence that you are detecting a crossing. So I will say that for now that we are happy to say that the binning is consistent with what we are finding in WWA. But I think the crossing will be a very interesting question later on, as if we get to declare that there is actually evolving dark energy. I think that would be the next step. Yeah.
No, I think this is a super valuable plot because if the community is now on the page that we should look at models beyond lambda CDM, there's no guarantee that W0WA is remotely a good parameterization of how things are changing with redshift. And what you find as a 4 sigma evidence in W0WA, in principle, could have been 20 sigma in a much better parameterization. But this is showing that perhaps W0WA is actually a relatively good parameterization for whatever is being seen in the data.
Finally, let me touch base on neutrinos, because we are also able to get constraints on that. Let me explain you how. So in this plot here, you are seeing in the x-axis omega m values, and in the y-axis you can see the constraints on the neutrino mass parameter. So in this plot, I'm showing you only CMB, and you can see that there is this well-known degeneracy between omega matter and the values of the neutrino mass parameter. So this is telling us that if CMB would like to have a very large omega matter value, then it will actually prefer to have more massive neutrinos compared to if it likes a lower omega matter value. The very nice thing here is that we can add a contour just coming from DESI constraints, and this is on the lambda seed model. And basically here, what I'm showing you is that DESI by itself cannot constrain the neutrino mass parameter, but it can set a constraint on omega matter. And so therefore, it can help you to break this geometrical degeneracy that is intrinsic from the CMB. And I guess people already can be guessing that if DESI likes this omega matter value, then the constraints are unavoidable going to fall in this region. And so probably it will be best if I show the 1D posteriors and tell you the constraints that we are obtaining right now. So the joint constraints from DESI plus CMB are that we get that the neutrino mass parameter should be less than 0.0642 eV at 95% confidence if we use DESI CMB coming from PR4 ChemSpec. However, contrary to what we observe in dark energy, here we are a little bit more sensitive to which CMB likelihood we use. And so we actually provide another more conservative constraint, which is using CMB lollipop and highlipop, in which we get the neutrino mass parameter to be less than 0.0774 eV. However, it will be in people's head that we'll be kind of getting too close to the lower terrestrial limit bound. And so given all the noise that we are doing about dark energy, we are, of course, it's very natural, and we are forced to include a contour plot like this, in which we are showing the DESI plus CMB constraints on the neutrino mass parameter if we go to a more generalized background given these W0 and W parameters. For this one, it is very important because here there are three very good details to comment on. One is that now the constraint of the neutrino mass that we get at 95% is an upper bound of less than 0.163 B. The second thing is that these constraints on neutrino mass depends a lot on the background that you assume. And so if we go to this more general background that we have actually arguments to go for that one, we actually allow for a more wider range of masses. And finally, that even now we can see a peak on the positive region if we use DESI plus CMB, which is actually what one will expect to see later on. So this actually is helping us to feel more confidence on this WNOWA model as well indirectly.
Does adding the supernova here reduce degeneracies and other parameters that then affects this plot here or not? Or
if we include rather WNOWA, then we actually have a big effect on the take on neutrino masses. So in the case of, if we add supernova here to this plot, what we will see is that the contours, they shift a little bit to the left. However, given how wide the error bars are, we still allow for I believe, both hierarchies to not be in trouble.
Great. That leaves us with a lot of interesting things to digest, but let's have a look to the future now. What is coming in the near future and perhaps even the longer term future?
One thing I'd like to emphasize just to start off is that it's pretty remarkable that we have these results already ready to share with you today. We've released our DR1 results on BAO measurements a little bit less than a year ago, and we only finished collecting the data for DR2 less than a year ago as well. So in less than 12 months, we've uniformly reprocessed 3 years of data, created catalogs and synthetic data sets, improved our analysis codes, measured BAO, and wrote these 2 key papers and 5 additional supporting papers. And this was only possible because our collaboration was, first of all, just super excited about the results that we found in DR1 and wanted to see what was going to happen with the DR3 analysis, and also because many people have devoted a huge fraction of their time to getting us to the point where we have these results to share. And as far as what's next on the horizon after that, after these results, we have a lot of additional analysis that's still to come. We have additional results still to come out on DR1, as well as many results that we'll still publish based upon the DR2 dataset, and that will include the full shape analysis, as well as additional papers beyond that. We'll also have several future data releases. We were originally planning on DESI as a 5-year survey, and after 5 years, I expect we'll have a DR3. And we have plans for an extension to DESI that would take the survey for an additional 2.5 years. That would take us until the end of 2028. And further into the future, we're hoping to operate DESI at the MAO, maybe with some minor instrument upgrades that will improve the sensitivity, particularly in the blue, and focus primarily on the Z greater than 2 universe, just like the current DESI experiment primarily focuses on measurements below about a redshift of 1.5. The science goals that we have in mind for DESI 2 include studying early dark energy and studying the growth of structure in the matter-dominated regime, as well as studying the nature of dark matter, including with substantial numbers of spectra of stars in the Milky Way that we can use to map the mass distribution of the Milky Way's halo. This DESI to DESI 2 transition will also allow us to have lots of great synergies with experiments that are just starting up, as well as that will be starting over the next few years. And that will, of course, include Rubin, and it will also include the Euclid results. It will also include results from the future Roman Space Telescope and CMB-S4, among other experiments, including lots of additional measurements of supernovae in particular. Further into the field, there are many of us within the DESI collaboration and outside of DESI that are working on the design of a next-generation facility called Spectroscopic Stage 5, or SPEC-S5. And the focus of SPEC-S5 would be on primordial physics and dark matter, targeting both the Z greater than 2 universe with Lyman break and Lyman-alpha emitters, as well as studying the dark matter halo of the Milky Way and nearby galaxies with stellar kinematics. And this The current concept for SPEC S5 is to have two 6-meter diameter telescopes, one in the northern hemisphere and one in the southern hemisphere. And our hope is that this facility would come online sometime in the 2030s.
Something that might be very, very interesting is, as you said, you've now released DR1, and it would be very interesting to see what the community now finds, especially seeing as you are seeing evidence for new physics. Like what models does the community find interesting? Now it suddenly becomes democratic and we don't have to rely on what DESI have chosen to look at. You've shown that with BAO or DESI BAO plus supernova, there's evidence for W0 WA, and DESI, well, plus the DES 3x2 point. And you've shown that DESI BAO plus CMB has evidence. There's one common rung there. Am I right to assume that Euclid will eventually, if this is real, we'll also be seeing it?
Yeah, because they also measure, they will also measure BO, I believe, right? So then that'll be the case. And but I don't know if with 1 year of data, that I'm not actually aware. But probably the trend they can confirm. That'll be a boom as well. Yeah.
Thanks everyone for watching. If you liked this and want to know more about DESI and how they measure BAO, you should check out last year's video. If you want to know about other DESI science, you should check out the full shape one from last year, where some other DESI scientists explained why these deviations from lambda CDM that they're seeing probably aren't due to a breakdown in general relativity. Other than that, thanks Cristhian and Paul for the great talk, and all of DESI for the great work.
Now, I'll just add thank you very much, Sean, for the great conversation. We appreciate the opportunity to share these exciting results with you and all the people who watch your channel, and it's great to be here.
Yeah, thank you very much, Sean, as well, for the invitation. Thank you.